Hello guys, good day. Welcome to today's lectures, and we're going to be looking at the solutions to four of this exact equation problem. Now I want you to take note that prior to this video I have released two videos introducing us to exact equations. The first one will give you the background you need to know about exact equations. The second one will take it a step further by teaching you how to do implicit differentiation and partial differentiation. Now, with this third lecture, we are going to learn how to solve exact equations. So each of these problems are going to be four different examples that will give us the background we need to understand in solving exact equations. So by the end of this video, I'll now summarize by laying out the rules that you need to take note of when you are solving exact equations. So if you're ready with your pen and with your paper, let's dive into the solution of these problems, starting with problem 1. Okay guys, welcome to problem 1, and in problem 1 we want to solve the exact equation exponential x sine y minus 2y sine x dx plus exponential x cos y plus 2x all into dy, and it is equal to 0. So this is usually how exact equation comes, but a more better way of presenting the questions to you will be giving this particular differential equation, test for its exactness, and solve for the general solution. So usually there are two things you want to do whenever you're given any problem in the particular form m the x plus n dy equal to 0. So whenever you're given a problem like this, there are two things you want to do. Number one is you want to test for exactness, and second thing you want to do is you want to solve for the solution. And by solution I mean general solution or particular solution. If it is in the case where you're given an initial value problem. Okay, so for this particular question, it's only a differential equation that we can see here, so we are going to be looking for the general solution. So the first thing is we are going to test for exactness. Okay, so we are going to test for exactness. Now you're given this differential equation exponential x sine y minus 2y sine x dx plus exponential x cos y plus 2 cos x dy equal to 0. Now that you're given this differential equation, so the next question is how do we test for exactness? So the first thing I want you to do first of all is you need to follow this general form. Make sure that this differential equation is put exactly in this form. Okay, the dx first, the dy first, so m then the n. So m in this case becomes this term over here, so exponential x sine y minus 2y sine x, and n becomes exponential x cos y plus 2 cos x. Is that okay? Since we have obtained our m and n, remember the condition for exactness. So for exactness, my should correspond to nx, and of course my is the partial derivative of m with respect to y. So we're going to evaluate that. Now this is our m, and we want to find partial derivative of m with respect to y. So please remember that when you're evaluating partial derivatives, okay, with respect to one variable, it means that that particular variable that you are differentiating with respect to partially will be the prevailing variable, while all other variables will be treated as a constant for the time being. So in such a scenario, as you have m here, exponential x will be a constant because x itself is a constant for the time being. And why is x a constant for the time being? Because we are differentiating partially with respect to y. So this is the only case when x will be a constant for the time being, because you're differentiating partially with respect to y. So if I differentiate this first term over here, exponential x remains as it is, not because I differentiated it, because it is a constant. Okay, so you're not going to touch it. You're just going to differentiate sine y, which is cos y, then minus. Now when you go over to this term, the constants are minus 2 and what? Sine x. They are both constants since x is a constant. So your focus is just to differentiate this y over here. When you differentiate y, you get 1. Okay, so minus 2 times 1 times sine x gives me a minus 2 sine x. So this is our my. Now our nx is partial derivative of m, which of n, sorry, with respect to x, and that is going to be, so let's do it together. So remember, y is now a constant in this case. Since y is a constant in this case, exponential x, when you differentiate it, you get exponential x. So you leave this cos y the way it is because y is a constant. Then when you differentiate 2 cos x with respect to x, you get minus 2 sine x, because of course when you differentiate cos x, you get minus sine x. So at the end of the day, we can now observe that my is equal to nx, and they are both equal to exponential x cos y minus 2 sine x. Hence the equation, that's the differential equation, is exact. So now that we have tested for exactness, the next thing, step 2, okay, step 1 is test for exactness. Okay, so this is step 1. You want to test for exactness. So anytime you're given an exact problem, you carry out 2 steps, test for exactness. Then step 2 is to solve. Okay, solve for the general solution or for the particular solution. So how do we solve for the particular solution? This is how you go about it. Now, to solve for the particular solution, we are going to assume a multivariable function phi of x comma y equal to c. So phi of x comma y is a multivariable function that will contain our general solution, and it is equal to c, which is an arbitrary constant. Now if you're wondering where this came about, please go and see the first 2 videos that I made on exact equations. There is part 1, there is part 2, this is currently part 3. So you want to know more about how phi of x comma y came about, please try to watch the playlist for part 1 and part 2, where I laid the background for exact equations, so you understand where phi of x is coming from. Now in part of what I established in the previous video, I said that this phi of x comma y is a multivariable function and it satisfies this particular condition. When you differentiate phi with respect to x, you're going to get m. Yes, this same m that we have over here, this same m that we have over here. And when you differentiate this phi with respect to y, you're going to have n, and yes, of course, the same n that you have over here. So the multivariable function that will contain our solution should be able to satisfy these particular conditions after we test that the differential equation is exact. So now to proceed further in our solutions, you can see that at this point you have 2 ways of applying separable variable technique in order to obtain phi, because our objective is to obtain this phi of x comma y at first that contains our solution. So the first way to obtain phi is either you could take it from m delta phi. When you separate the variables, you now have m delta x. So you're now going to integrate. Okay, integral of del phi is equal to integral of m del x, and this place will now give me when you integrate del phi, you're going to get phi of x comma y, okay, is equal to, so we don't yet know what this one is, but this is what I'm going to do. I'm going to integrate this put this integral sign, and I'm going to put an x here, and I'm going to put an m, change it to dx. So the essence of doing this particular writing it in this particular form is that we are carrying out this integration, taking note that it's not like the conventional integration that we know. We are kind of like doing partial integration, and when you're doing partial integration, this time x is actually the prevailing variable on this side. Is that okay? X is the prevailing variable on this side, so you're integrating partially with respect to x. Now you will see how the solution will turn out when I proceed with the solving later. But another person could decide to carry out his variable separable technique using n in this way. So if you integrate both sides, you now get your phi of x comma y. In this case, you can integrate partially with respect to y, so n dy. So this integral, when you integrate it in this way, you're actually taking y, is that okay, to be the prevailing variable, then you're holding x to be a constant for the time being. So we are going to see how we'll proceed. So anybody can take m or anybody can take n. There is no specification as to which one you should take, but this is my advice. Use your eyes to see which one is easier and pick whether you use m or whether you use n. If you notice that the form of m is more complicated for you to integrate, please check n. N might be simpler, and vice versa. If you discover that n is more complicated for you to integrate, check m. M might be simpler, and go for m. So for this particular one, let me look with my eyes and see what my choice will be. Now looking at m has exponential x sin y minus 2y sin x, but n has exponential x cos y plus 2 cos x. So this one kind of seems more appealing for me to integrate, because it has lesser variables. Okay, unlike this one, the count of variable, I'm seeing exponential x sin y, then 2y sin x. Wow, this looks so complicated for me. But this one, I'm just seeing exponential x cos y, then a 2 cos x. So I'll rather go with what, this particular n, and let me show you how I'm going to do that. So I want to use n over here to determine phi of x. Remember, you can use the integral of m with respect to x partially, or the integral of n with respect to y partially, to determine phi of x. Okay, so whichever one you want to choose, no problem. So I want to choose n in this case, and is equal to integral respect to y. So the n that I'm looking at is exponential x cos y plus 2 cos x. Exponential x cos y plus 2 cos x. So I'm integrating partially with respect to y. Now follow me carefully. Let's do the integration together. Now when you're integrating partially with respect to y, remember that x is actually acting as a constant. So anything about x, exponential x is a constant, 2 cos x is a constant in this case. Okay, so you have integral of phi of x comma y now becomes, so starting with this term, when you integrate this term, just imagine that this exponential x is a number. For instance, let me say I'm integrating 2 cos y with respect to y. It's still the same thing as 2 integral of cos y dy, and this will give me 2 sine y. Okay, because when you integrate cos y, you get sine y. So integrating this term out with respect to y partially, it will be exponential x sine y. Okay, so why am I still leaving exponential x here? Just like I said, it's a constant, so you're not supposed to touch it. Okay, you leave it the way it is. Now going over to this one, you can see this whole 2 cos x as a constant. So whenever you integrate a constant with respect to y, what you're going to get is ky. Is that okay? Ky. So in this case, when we integrate the whole of this constant with respect to y, we'll have 2 cos x times y, which can be actually 2y cos x. Is that okay? Then remember your constant of integration in this case. But here is something interesting that happened when we are putting the constant of integration. When we are putting the constant of integration, we are going to assume that the constant of integration is actually a function of x in this case. Okay, so h of x is the integration constant, and the integration constant is actually taken to be a function of x. So it makes sense to assume that the integration constant is a function of x, because when we differentiate partially again, when we differentiate this particular phi of x partially with respect to y, you discover that if you differentiate this term with respect to y, we'll get this. If you differentiate this term partially with respect to y, you will get this. And when you differentiate this term partially with respect to y, since it is actually a function of x, it is actually a constant, so it will cancel out. Is that okay? So it makes sense that when you're integrating partially with respect to y, your integration constant will not just be a direct constant, but rather it will be a function of the complementary variable, which in this case is x. Is that okay? So if we continue in this vein, we have now gotten up to a very good point. Now you don't stop here, because you need to take a step further to determine what h of x is. How do you determine h of x? First of all, you need to differentiate. So we differentiate phi of x comma y partially with respect to x. So when you differentiate it with respect to x, now remember you integrated with respect to y partially, so you're going to differentiate with respect to x. If on the other hand you integrated with respect to x partially, you're going to differentiate it now partially with respect to y. So I'm following the route where I integrated partially with respect to x, so I want to differentiate. I integrated partially with respect to y, so I want to differentiate partially with respect to x, and this is what I want to differentiate partially with respect to x. So if we differentiate it, starting with this term, since sin y is a constant, and when you differentiate exponential x, you will still get exponential x. So sin y stays as it is. Then when you differentiate this particular term, 2y cos x, with respect to x partially, y is a constant, so it will stay untouched. 2 is a constant, so it will stay untouched. When you differentiate cos x, you get minus sin x, so you get minus 2y sin x. Then when you differentiate h of x, you're going to get h prime of x. Is that okay? Now, according to our rule, do you remember that the establishment says that anytime we differentiate the phi with respect to x, we are going to get m? Is that okay? So we are trying to say that this is equal to m. So we now need to look for the expression we had for m, and the expression we had for m over here is this. M is exponential x sin y minus 2y sin x. So exponential x sin y minus 2y sin x plus h prime of x is equal to m, and m is exponential x sin y minus 2y sin x. Now watch what happens if you solve for h of x, making h of x, h prime of x rather, the subject of the formula. You have exponential x sin y minus 2y sin x minus the whole of this thing over here, just carry it at once, exponential x sin y minus 2y sin x, and you discover that h prime of x will be 0. Of course, everything cancels out, so h prime of x equal to 0. That means dh dx is equal to 0 in this case, or dh is equal to 0. So if you do something like this, dh is equal to 0 dx, for instance. So this 0 dx, when I'm treating it like this, I'm not going to actually multiply directly, because I want to integrate. Okay, I want to integrate. So you're not going to multiply 0 times dx is equal to 0. No, you just want to integrate it now, okay, for integration's sake. So when we integrate the h, we are going to get h of x, okay, and when we integrate 0, we'll get a constant. Okay, when you integrate 0, you get a constant, because actually whenever you differentiate a constant, you're going to get 0. So when you integrate 0, you get an arbitrary constant. So we have now established, okay, from this particular series of steps, that our h of x is equal to what? A constant. That our h of x is equal to a constant. So where does this h of x applies? It applies here now. So this is our answer. Okay, this is our half-baked answer, if I'll put it like that. So okay, recall that phi of x comma y is equal to, so let me just see, exponential x sine y minus, okay, it's actually a plus 2y cos x plus h of x. Now you also have to recall that this phi of x comma y is equal to an arbitrary constant. Are we together? So thirdly, you have to recall that h of x is equal to k. Is that okay? So 3 recalling at once. So these are the 3 major things. You want to find the expression for phi of x, which will also contain a h of x or perhaps a h of y, whichever way you started. Then the next thing is you also want to recall from your key assumption that our multivariable function is a constant function. That means it's equal to an arbitrary constant c. And since we've determined the value for h of x to be a constant, we want to now substitute all this particular stuff into this equation over here. So our phi of x comma y is equal to c, then exponential x sine y plus 2y cos x, then plus h of x is now k. Is that okay? So when you evaluate it, you have exponential x sine y plus 2y cos x is equal to c minus k. And finally exponential x sine y plus 2y cos x is equal to, let me say, c minus k is another arbitrary constant, so where a is equal to c minus k. Okay, so this is now your final general solution. This is the general solution. So general solution, okay, for the differential equation above. So thank you very much for staying with us up to this time. We have actually said a lot of things, but when I solve the remaining 3 examples, I believe you get conversant with the steps. So in this particular example, I started with I obtained my phi of x by integrating with respect to y, right? So in the next example, I'm going to alternate it. I'm going to integrate with respect to x, and next one I'll alternate again, and I'll alternate. So you on your own, to make your hand strong, you can actually alternate this particular example. Since I integrated with respect to y, I want you to on your own integrate with respect to x. That means at this point, I'm talking at this point over here, I followed this step. So I want you to follow this step and see that you also arrive at the same answer if you follow everything that I have taught you so far. Okay, if you follow everything that I have taught you so far. So I'm going to be showing you guys something interesting at the end of all of these particular video that you have seen. But first of all, tighten your belts as we go to the next problem. Okay, so let's go. Okay, this is problem 2. In problem 2, we have to check for the exactness of this long differential equation you're seeing over here: y exponential xy equals 2x minus 2 exponential xy sine 2x plus 2x all into the x, then plus x exponential xy equals 2x minus 3 all into dy equal to 0. So after checking for the exactness, then we have to find its general solution. So we're going to check for exactness. Okay, so step 1 is test for exactness. And what is the condition given for us to test for the exactness of this equation? To test for the exactness of this equation, remember the condition that for a given m dx plus n dy equal to 0, my should be equal to nx. Now these are subscript. M subscript y should be equal to n subscript x. Of course, we all know that for the differential equation given to us, this differential equation, y exponential xy cos 2x minus 2 exponential xy sin 2x plus 2x all into dx, then plus x exponential xy cos 2x minus 3 dy equal to 0. For this particular differential equation, our m is y exponential xy cos 2x minus 2 exponential xy sin 2x plus 2x, and our n is x exponential xy cos 2x then minus 3. So we want to find my, and my is the partial derivative of m with respect to y. So let's begin from this point over here. So we are taking the partial derivative of m with respect to y. So look at this particular first term over here. You can see a y and an exponential xy. So you are going to use product rule over here. Okay, there is a product terms, two separate y terms here, so we have to use product rule. Remember, when you're taking partial derivative with respect to y, x is going to be taken as a constant for the time being. Now this is how I'm going to organize y exponential xy cos 2x in order to check for its exactness. I'll take the whole of this as my v term, and I'll take the whole of this as my u term. So remember the law, u dv plus v du. Is that okay? So u dv plus v du, that's product rule. So doing that, u is y, then dv, you're differentiating the whole of this term partially with respect to y. And clearly, if you do the differentiation correctly, you remember that cos 2x is a constant, so it will remain untouched. Now the challenge is exponential xy. When you differentiate it partially with respect to y, do you know that you're going to get x exponential xy? Okay, it's just like you're differentiating exponential ax. Okay, when you differentiate exponential ax, you get a exponential ax. Or when you differentiate exponential ay with respect to y, you get a exponential ay. Okay, now that we are differentiating exponential xy with respect to x, with respect to y, I'm sorry about that, you're differentiating exponential xy partially with respect to y, so you're going to get x exponential xy. X is taken as a constant, so you have yx exponential xy, then cos 2x, then plus, we now have v du. So v du in this case will repeat the exponential xy cos 2x, because that is the v term. Okay, then when we now differentiate our u, which in this case is 1 y, since you're differentiating y with respect to itself, you're going to get 1. Is that okay? So if you differentiate y with respect to y, you get 1. Is that okay? So we finish this particular term over here. We finish differentiating it. So going over to the second term, I now have minus. Now when you differentiate minus 2 exponential xy sin 2x partially with respect to y, okay, you're going to get 2x exponential xy then sin 2x. Okay, so this x is just coming down from this point like we established earlier. And when you differentiate this last term over here, since it is a term all in x, it will cancel out because it is a constant. So this is the derivative. Okay, for my, we're having, let me just rearrange it. I have x y exponential xy cos 2x, then I have plus exponential xy cos 2x, then minus 2x exponential xy sine 2x. So this is the outcome for my my. So the next thing I want to do is my nx. And nx is the partial derivative of n with respect to x, and n is already staring us over here, this particular place. Okay, so there's a problem here. For nx, we have x appearing in 3 different terms, in this term here, in this term here, and in this term here. So how am I going to differentiate it? What kind of product rule am I going to apply here? So the product rule I'm going to apply here is going to be a chain product rule. Take note of my language, a chain product rule. So if you consider x exponential xy cos 2x and you want to differentiate it with respect to x now this time around, okay, partially with respect to x, so the product rule you're going to apply is a concatenated or a chain product rule, and I'm going to explain that. So I'll take the whole of this term as my u, okay, and I'll take the whole of this one as my what, v. So I'll now apply the rule u dv plus v du. Now let me see what happens when I apply the rule. So my u is going to be x exponential xy, then my dv, I'm going to differentiate cos 2x with respect to x partially, and of course it will give me minus 2 sine 2x minus 2 sine 2x. Okay, then I have satisfied the u dv. Then I'll now go to v du. Then for v du, I have plus cos 2x v du. This is v. Then du is actually the derivative of this guy over here, x exponential xy. So let me just put a prime on it to indicate that we are going to differentiate it with respect to x. So when you now move over to this term over here, it's minus 3. If you differentiate it with respect to x, it cancels out. So now you will see where the concatenated or the nested chain rule will apply. So since these two terms now, you want to differentiate this one, and you discover that there is another product in x and exponential xy. Okay, there are terms in x, so we need to differentiate them with product rule again. So I'll now apply product rule again to this place. Okay, so nx is, if I arrange this one, I'll have minus 2x exponential xy, then sine 2x, then plus cos 2x into, okay, so we want to differentiate this one now. Okay, with respect to x, I'll take x as my u and exponential xy as my v. So u dv x, then when you differentiate this particular term partially with respect to x, that's your dv, you're going to get y exponential xy, because y is a constant and the derivative of exponential ax is actually a exponential ax. Typically, whenever you're differentiating with respect to a variable, all constants become coefficients after differentiating. So when you differentiate exponential xy, since y is a constant, it will come down and you now repeat the exponential xy term. So this is u dv, then plus v du, that's exponential xy as our v, then du, when you differentiate x, you get 1. Is that okay? So we are now going to open the bracket carefully and see what we get. So nx is negative 2x exponential xy sine 2x, then plus, opening this bracket, I'll have xy cos xy first of all, then exponential xy cos 2x, then plus exponential xy cos 2x. Okay, so this is what we have for our nx. So should we compare it with our my and see if it is actually the same? Okay, so I can see this term in my and I can also see it here. Good. I can see a minus 2x exponential xy sine 2x, and I can see minus 2x exponential xy sine 2x, and I can see xy exponential xy cos 2x. and I can also see xy exponential xy cos 2x. Hence my is equal to nx. And the equation is exact. Okay, since the equation is exact, we now go to step 2, the general solution. So how do we obtain the general solution? Remember, this is how you always start when you want to obtain your general solution. So we're going to assume a phi of x comma y, a multivariable function equal to an arbitrary constant, okay, such that the partial derivative of phi with respect to x is the m that we have above, and the partial derivative of phi with respect to y is actually our n. Okay, so if we do it in this case, we can see that phi of partial derivative of phi is equal to m dx. Let's say we want to use the method of variable separable, and also partial derivative of phi is equal to n del y. So if you integrate both sides, integral of m del x and integral of del phi is, let me say, integral of n del y. So there will be some transformations here. This particular left hand side becomes phi of x comma y, and this becomes an integral with respect to x, then m dx, and this particular one becomes phi of x comma y is equal to an integral with respect to y. Okay, we have n dy. Okay, so you see the changes from this point to this point. So the meaning of this particular change is just to let you know that this integral, it's like a partial integration. It's not like a normal conventional integration. So in this first case, we are integrating with respect to x partially, or in this case, you're integrating with y partially. So you can see that phi of x comma y, the multivariable function, can be gotten either by integrating m partially with respect to x, or by integrating n partially with respect to y. So whichever one you want to use to get phi of x comma y, that is at your own discretion. But remember what I said in the last example. I told us that you have to choose the one that is much more simpler and much more lighter. Now look at our m and look at our n over here. So you can discover that for n, which we are going to integrate with respect to y, there are actually let me put it like this: we have lesser difficulty if we take the integration from n than if we take it from m. So in m, you're integrating with respect to x, right? Okay, according to the solution, what we have over here. For m, you're integrating partially with respect to x, but for n, you're integrating partially with respect to y. Now look at the expression for m. If we decide to go and integrate partially with respect to x for m, we are going to get the same answer, but the process will be very long. So you have to start applying integration by parts for this particular term over here. Not just that, you have to apply another integration by parts, because you're integrating partially with respect to x. So you definitely apply integration by parts. But look at this one now. You're integrating with respect to y, okay, in this particular case of n. Since you're integrating with respect to y, remember, partial integration, x is a constant, therefore cos 2x is a constant, and the only thing we have to do with is this. The only thing we have to deal with is just the exponential term, because it's the only term that contains y. So if you ask me, I'll choose n. I'll like to despite the fact that I said we may alternate, I'll take the integral of with respect to x in this case, then take the integral with respect to y in the other case. For this example, it will be safer for us to go with n, so that it will reduce the procedures for us. So n is x exponential xy cos 2x minus 3. So this is how I'm going to write it. So choosing to obtain our phi of x comma y using this integral with respect to y for n dy, where n is x, what did we say, x exponential xy cos 2x minus 3, x exponential xy cos 2x and minus 3. So this is my what, n in this case. Okay, so this is my n. So I'll now say phi of x comma y is equal to the integral partially with respect to y, so x exponential xy and cos 2x minus 3. So this is with respect to y. So let's do it together. Our phi of x comma y is equal to, remember you're integrating partially with respect to y. Okay, so when you integrate partially with respect to y, remember integrating partially with respect to y, let's say I have the integral of exponential ay with respect to y. If I integrate this with respect to y, where a is a constant, I'll get exponential ay over a. Okay, so the same thing will happen here to this term. So you don't have to worry about x or cos 2x, they are both constants, so they will stay. Okay, so you have x, and you now integrate this particular term with respect to y, and you're going to get exponential xy over x, then cos 2x minus 3 with respect to y, right? So you have minus 3y in this case, then plus our constant of integration. Our constant of integration is a h of x this time around. Okay, since we are integrating with respect to y, your constant of integration will be a h of x, but if you integrated with respect to x partially, your constant of integration will be a g of y. Okay, g of y and h of x. So I like using g for y and h for x. So this is not a convention, you can actually introduce your own letters. Okay, but these are just cool ways of doing that. So x cancels out x, and our phi of x comma y is exponential xy cos 2x minus 3y plus h of what, x. Okay, h of x. So remember that after you've gotten this expression, which will be our answer, but we're not going to stop here because this answer is not really complete as it is. You have to take a step further by differentiating it. So when you differentiate this phi with respect to x, remember when you integrate with respect to y, you differentiate with respect to x again, and the aim is to find h of x. So if you differentiate it with respect to x, you're going to get, let's differentiate it with respect to x. So product rule here will be u exponential xy, then dv dx. We are going to take our dv, and when you do this, you get minus 2 sine 2x, then plus v, which is cos 2x, then du. When we differentiate this one with respect to x, we'll get y exponential xy with respect to x. Then with respect to x, when you differentiate this term over here with respect to x, remember partial differentiation with respect to x, so 3y cancels out since it's a constant. So plus, when you now differentiate this one, you get h prime of x, okay, with respect to x. So remember that the assumption for phi of x comma y is such that when you take the partial derivative of phi with respect to x, you're going to get m. Is that okay? So we have for this place minus 2 exponential xy sine 2x, then plus we have y exponential xy cos 2x plus h prime of x is equal to m. So we are now going to compare this particular stuff over here on this left hand side with what m means on the right hand side. So minus 2 exponential xy cos sine 2x plus y exponential xy cos 2x plus h prime of x is equal to, so let's hustle for what m is. So m is actually given to us as this expression over here, y exponential xy. Okay, let me do some trick. I'll just copy it out so that it will be easy for us to see. Control C. So over here, let me just Control V, paste it and drag it over to this side. So this is our expression for m. Is that okay? So this is our expression for m. So this is our expression for m. So what can you notice from this particular expression for m? You will notice that minus 2 exponential x y sine 2x is common in both sides, so they can cancel out. So what else do you notice? Y exponential xy cos 2x is also common in both sides, so they will cancel out. So finally you'll be left with h prime of x is equal to 2x. So since h prime of x is equal to 2x, your h prime of x means dh dx is equal to 2x. So when you do separable variable, dh is equal to 2x dx, then h of x is now the integral of 2x dx, and this is going to give me x squared plus constant of integration. Okay, so when you integrate for h of x, you get x squared plus constant of integration. So we have found h of x finally. Therefore we'll now refer back to the first phi of x comma y we got. So therefore our phi of x comma y is going to be equal to, according to this expression over here, exponential xy cos 2x, exponential xy cos 2x, what is it next, minus 3y plus h of x. So minus 3y then plus h of x. So this is h of x, which is x squared plus constants. Now you have to recall, okay, this is not where you stop. Recall that your phi of x comma y is a constant function equal to c, and c is an arbitrary constant. Hence I'll replace this place with c. So c is equal to exponential xy cos 2x minus 3y plus x squared plus k. Okay, so when you solve in this particular way, taking the arbitrary constants or grouping the arbitrary constant, you have exponential xy cos 2x minus 3y plus x squared is equal to c minus k. So let c minus k be a, another arbitrary constant. So exponential xy cos 2x plus x squared minus 3y is equal to a, and this becomes our general solution. So this is the general solution for the problem that we were given above. Okay, so I want you to take notes of this particular solution. So I'm going to be demonstrating something with this solution to show you that it is actually legitimate, it is actually correct in every way. So thank you for hanging on to the end of problem 2. We're going to move on to another problem, problem 3, and we'll have one more problem 4. So trust me, this problem 2 is the hardest. Okay, problem 3 will be much more easier than this. So let's go to problem 3. Okay, here we are at problem 3, and in problem 3 we are to test for the exactness of 2y minus x, 2x minus y all into dx plus 2y minus x all into dy equal to 0. So having tested for the exactness, we are to solve for the primitive. The primitive is another word for general solution. Okay, so let's begin. So we are given 2x minus y dx plus 2y minus x dy equal to 0, and we want to test for its exactness. So step 1 is test for exactness. So do you still remember to test for exactness? So for m dx plus n dy equal to 0, whenever we're given a differential equation in this form, the condition for exactness my should be equal to nx. Okay, so my is partial derivative of what? M with respect to y, and this clearly is our m. Okay, so m is 2x minus y and n is 2y minus x. So we are going to differentiate m with respect to y partially, with respect to y partially. So if you differentiate 2x with respect to y partially, what happens? It cancels out since x is a constant for the time being. So when you differentiate minus y, you get minus 1. Okay, so ny is the partial derivative, sorry, I said ny, nx this time around is the partial derivative of n with respect to x, and of course when you differentiate 2y with respect to x partially, you get 0. When you differentiate minus x, you get minus 1. So we have that our my is equal to nx and they are both equal to minus 1. So hence the differential equation is exact. Now if you are very sensitive to this differential equation, you will discover that it is also looking like one of the homogeneous differential equations that we solved in the past. Okay, so it is actually homogeneous differential equations in the sense that if you make dy dx the subject of the formula, dy dx is going to transform into minus 2x minus y divided by 2y minus x. So this is going to be dy dx, and clearly this is homogeneous. When you carry out the lambda test, you discover that this is homogeneous. So if you are like totally new to homogeneous differential equations, I have also prepared a video on, like a full video on with detailed explanations about homogeneous differential equations. So please go back to the playlist and watch it. But this differential equation, in as much as we have confirmed that it is exact, it is also homogeneous. Okay, it is also homogeneous, and the degree of homogeneity is 1 in this case. So you can actually use the substitutions y is equal to vx to solve it, and you still get the same answer as we will get if we use the exact approach. But since we're in the domain of exact equations, I'm not going to solve it using homogeneous differential equations. I'll solve it using the exact equation technique. So we have verified in step 1 that it is exact. So step 2, we now want to what? After verifying, we want to find the primitive or the general solution. So if you want to find the primitive or the general solution, remember, assume, that's the first step. So assume a phi of x comma y equal to a constant such that the partial derivative of phi with respect to x is m, and the partial derivative of phi with respect to y is n. So with these assumptions, you now get in the long run that that phi of x comma y can be gotten when we carry out this integral with respect to y for m, partial integration, or phi of x can be gotten when you carry a partial integration with respect to x for n, so just like we've established in the past, you will discover that our phi of x comma y can be gotten in two ways. Way one is when you integrate partially with respect to x m, or when you integrate partially with respect to y, your n. So whichever one you want to follow to get your phi of x comma y is up to you. Okay, so let's look at the expressions for m and for n. Okay, the expressions for m and for n seem pretty much like easier. Okay, they are kind of like balanced in terms of the contents of the x and the y terms respectively, so I can actually use any one I want. And this time around, since I've been working with y, we've been integrating with respect to y, I'm going to integrate with respect to x. That means I'm going to choose m is 2x minus y. So we have integration with respect to x, 2x minus y dx, partial integration, okay, in this case. So you want to integrate with respect to x using the m approach, since all this while in the first and the second examples we used n because n was much more easier to work with for our case. So since m and n are balanced in this case, no one is harder than the other, or no one seems more complicated than the other. We just want to use m so that you see how like integrating from the x angle is going to be. Now that I have chosen phi of x y to be the integral with respect to x of 2x minus y, so we are going to integrate partially with respect to x. So if you integrate this term 2x, I believe you're going to get an x squared. Okay, when you integrate 2x, you get x squared, because integral of 2x dx is 2x squared over 2. Okay, so this one cancels out and you're left with x squared. So when you integrate a constant, which in this case is y, an x term will be added to it. Okay, so let's just call it xy, then our constant of integration. So constant of integration in this case is a function of a complementary variable, which in this case is y. Okay, so you have a g of y. Okay, so our g of y is an unknown which we are going to attempt to find, but this is like the half-baked answer. This is your half-baked answer. So in order to find g of y, you have to take a step further by differentiating your phi of x with respect to what? Y, of course. Remember, if you integrate partially with respect to y, then to find the unknown function, you have to differentiate with respect to the complementary variable. We integrated with respect to x, so we're going to differentiate with respect to y partially. So when you differentiate this first term with respect to y, x squared is a constant, so it goes away. So when you differentiate this one with respect to y, you're going to get minus x, because x is a constant. When you differentiate g of y with respect to y, you're going to get g prime of y. Is that okay? G prime of y. So this is, of course, partial derivative of phi with respect to y should be equal to what? N. According to this an assumption that we made, partial derivative of phi with respect to y should be equal to n. And what is the expression for n? The expression for n, according to our system, is 2y minus x. 2y minus x. So therefore, minus x plus g prime of y is equal to 2y minus x. So minus x happens to be common in both hands of the equality, so they will cancel out, and g prime of y, which is dg dy, is actually 2y. So when you do separable variable in this case, dg becomes 2y dy, and when you integrate dg, you're going to get integral of 2y dy. So integrating the dg, you're going to get your g of y is going to be equal to, integrating 2y, you're going to get y squared plus a constant of integration. Okay, now this constant of integration is a pure constant, it's not a function. Now that you've gotten the unknown function g of y, you're going to plug it back into our equation star over here, so that our phi of x comma y is going to be equal to, we had x squared minus xy plus g of y, okay, plus g of y, which in our case is y squared plus k. So this is not where you're going to stop. You have to recall that our phi of x comma y is a constant function. Okay, c is an arbitrary constant, therefore c is equal to x squared minus xy plus y squared plus k. So as usual, x squared minus xy plus y squared becomes c minus k. So let c minus k be a, for instance, since they are both arbitrary constants. So we now have x squared minus xy plus y squared will now be equal to a as the final solution, or the primitive or the general solution for the problem that we are given. So example 3 is pretty much straightforward. Problem 3 is straightforward. Okay, so I hope you understood. So if you had integrated with respect to y and you differentiated with respect to x partially, you still get the same answer. So I'll leave that to you to attempt on your own. So in the meantime, let's go over to problem 4 and see the solution. Problem 4 is the last, after which I'll just summarize the steps in tackling exact equations. Okay guys, here we are at problem 4, and in problem 4 we are given the differential equation to test its exactness and hence to find its particular solution for a given initial condition y of 1 equal to 0. So first of all, we are given 9x squared plus y minus 1 dx minus 4y minus x dy is equal to 0. So this differential equation is not in the form m dx plus n dy equal to 0, but it can be. Okay, the reason is because of this minus sign, and according to the general form there is a plus sign here. So how do we introduce a plus sign in this case? So it can be rewritten as the differential equation can be rewritten as 9x squared plus y minus 1 dx. So if you use this minus to open the bracket, you're going to have a plus x minus 4y dy equal to, what do you have? 0. So it is now in the form m dx plus n dy. So where m is 9x squared plus y minus 1 and n is going to be x minus 4y. So for exactness, we have m subscript y should be n subscript x, and of course we know that my is the partial derivative of m with respect to y, which we are going to carry out here. So differentiating partially with respect to y, 9x squared cancels out since it's a constant. When you differentiate y, you get 1. When you differentiate minus 1, you get 0. So my is equal to 1. So, and nx is the partial derivative of n with respect to x, and of course this is our expression for n. So when we differentiate x with respect to itself, we get 1. When we differentiate 4y, negative 4y rather, we get 0 since y is a constant for the time being. Okay, so my is equal to nx is equal to 1. So the differential equation is exact. So we are going to find the solution. So step 2 is what? Particular solution. y of 1 equal to 0. Okay, for this initial condition. So this is an IVP. It's not just a differential equation problem, it's an IVP. You're giving a differential equation with an initial condition, so that makes it an IVP. So now that we have established that it is an IVP, so we want to solve for what's the particular solution. As usual, you're going to assume a phi of x comma y equal to some constant c, arbitrary constant, such that the
partial derivative of phi with respect to x is m, and the partial derivative of phi with respect to y is n. Okay, m and n are the same ones we have over here. Okay, so this arbitrary function that we are assuming should satisfy that whenever you differentiate it with respect to x partially, you get m, and differentiate it with respect to y, you get n. So as usual, we can establish from our proof that our phi of x comma y can be the integral with respect to x of m dx, or our phi of x comma y can be the integral with respect to y of n. Okay, like this. So whichever one you want to go with, please suit yourself. But now look at the expressions for m and the y and n. So which one is longer, which one is shorter? So which one would you want to probably start with? Okay, I know n is shorter in terms of length, in terms of number of terms. We have just 4x, sorry, we have x minus 4y. So ym is 9x squared, then plus we have y minus 1. So since in the last example I integrated with respect to x, I will also integrate with respect to x in this case, because in the first two examples I integrated with respect to y. So I just want to like balance things up, and the expression for m is not so complicated, so we can actually integrate it with respect to x. So phi of x comma y is equal to the integral partially with respect to x for our m, which is 9x squared plus 1 plus plus x minus what? Minus 1. 9x squared plus y plus y minus 1. So we are integrating with respect to x. So you can take it from here or from here. Remember, anyone, just look for the one that is better, easier, or better simpler for you. So we have phi of x comma y is going to be the integral with respect to x. When you integrate 9x squared with respect to you get 9x cubed over 3, then plus when you integrate y with respect to x partially, since y is a constant, you get xy, and when you integrate minus 1 with respect to x, you're going to get minus x. Then remember your constant of integration, which in this case is going to be an arbitrary unknown function g of y. Okay, g of y. So this is going to be leading up to our solution for phi of x comma y. So we'll have 3 cancels part of 9, you get 3x cubed plus xy minus x plus g of y. Is that okay? G of y. So this is our half-baked solution. Okay, our half-baked solution. So for this half-baked solution, our objective is to find g of y. To find g of I, we have to differentiate with respect to y. Okay, when you integrate with respect to x, you differentiate with respect to y partially. So when you differentiate this term with respect to y partially, it cancels out. Differentiate this term with respect to y, you're going to get x, since x is a constant. Differentiate this one with respect to y, it cancels out, and differentiating g of y, you get g prime of y. Okay, this g prime of y is dg dy, g of y dy. Okay, so remember that after differentiating, it should be equal to n, according to our assumption from the beginning, that our phi of x comma y is such that what, when you differentiate it with respect to y partially, you will get n. And where is the expression for n? The expression for n is x minus 4y, x minus 4y. So we now have that x plus g prime of y is equal to n is x minus 4y. So x is common on both sides, it cancels out. So this means g prime of y is equal to minus 4y. Okay, so when we get our g of y, we are going to integrate minus 4y dy, and our g of y is going to be what? Minus 4y squared over 2 plus k, which is actually negative 2y squared plus constant of integration. So this is our g of y. So what is remaining, just plug it into this over here. So phi of x comma y is equal to 3x cubed plus xy minus x plus g of y. So phi of x comma y is equal to 3x cubed minus plus xy minus x, then plus g of y plus negative 2y squared plus k. Okay, so g of x comma y is equal to 3x cubed plus xy minus x, then minus 2y squared plus k. So this is what we have as our g of x comma y. So recall that phi of x comma y, sorry, this is what we have for our phi of x comma y. Phi of x comma y is the constant function, so it's called to an arbitrary constant c. So you can replace this with c is equal to 3x cubed plus xy minus x minus 2y squared, okay, plus k. So when you rearrange, you get 3x cubed, okay, plus xy minus x, then minus 2y squared is equal to c minus k and is equal to a. Okay, when we assume a to represent c minus k, okay, so you have the general solution to be 3x cubed plus xy minus x minus 2y squared is equal to a. So it's the general solution, but we are given that y of what for this particular question, let me get it again, y of 1 equal to 0, okay, y of 1 is equal to 0. So y of 1 equals to 0 means y is equal to 0 and x equal to 1. So you're going to use it to find this arbitrary constant a. So anywhere you see x, you put 1, anywhere you see y, you put 0. 3 into 1 cube plus, you have 1 times 0 minus 1 and minus 2, 0 squared is equal to a. So when we solve, we'll have 3, okay, this 0, this is minus 1, and this is 0, and this is a. So a is equal to 2. So finally we now have, for this particular differential equation, 3x cubed plus xy minus x minus 2y squared is equal to, what do you have, 2. So this is the particular solution. Okay, welcome to this session where we now summarize what we've learned in exact equations so far. So to summarize the technique in solving every exact differential equation, first and foremostly, you'll be given an exact equation that you are to actually express in the form m dx plus n dy equal to 0. So step 1 is what? Is to test for exactness. And in testing for exactness, this criteria must be satisfied, that the partial derivative of m with respect to y should be equal to the partial derivative of n with respect to what? X. So there should be symmetry. Other people write this by saying m subscript y is equivalent to n subscript x. So there must be symmetry between your my and your nx terms, okay, if this equation must be exact. Okay, so this is the first criteria that must be satisfied. So after you verify that this differential equation is exact, step 2 is to what? Make the assumptions, okay? A phi of x That's introduce your multivariable function phi of x equal to c. Okay, c is an arbitrary constant such that the partial derivative of phi with respect to x is m, that's this m over here, and the partial derivative of phi with respect to y is actually n, this n over here. Okay, so after making these assumptions, you later discover that your phi of x comma y can be gotten with two approaches. The first one is when you take the partial integral of m with respect to x, or phi of x comma y can be gotten when you take the integral with respect to y of n. Okay, partial integral of n with respect to y. So these are two ways of getting what your answer. Now, assuming you decide to carry out the integration in order to discover what phi of xy is, using this first part, and during the course of the video you could either take this one or you could either take this one. What you just need to do is to figure out which expression is easier for you to work with. And in terms of expression, I mean the expressions for m and the expression for n. So I'll ask myself, is m easier for me to integrate with respect to x? If yes, I'll go with this first one. Or if m is difficult, I'll ask myself, is n easier to integrate? If yes, I'll go with n. Is that okay? So let me assume I chose to go with m. So what I'm going to get is phi of x comma y is equal to integral of m with respect to x partially. So my integration constant will be a function of y. Is that okay? My integration constant will be a function of y. So immediately, let me put this one in brackets. Okay, so this is the values of the integral and this is the integration constant. Immediately I carry out this integration, I'm going to differentiate this particular equation because this equation will contain my half-baked solution. So immediately I differentiate this equation now with respect to what? Remember, we integrated partially with respect to s. So this time around you're going to differentiate this same solution over here partially with respect to y. When you differentiate it with respect to y, you're now going to get d with respect to y, of the whole of this guy, the integral m dx, okay, plus you're going to get y prime g prime of y. Okay, so the next thing is you're going to equate this to what? N. That's correct, because when you differentiate your phi with respect to y, you get n according to the criteria that we established over here. So after getting this, solve for g of y. Okay, when you solve for g of y, you have to equate this whole expression to n. Then you're going to do some calculations, and when you get the value of g of y, you now plug it back into these equations. So assuming g of y is equal to some, let me say, f of y, for instance, because it will be strictly a function of y. Assuming you got g of y to be an f of y, so this f of y could be a function of y or it could be a constant. So what you're now going to do is you recall that your phi of x comma y is equal to c. Is that okay? So you will now change the nature of this equation from c is equal to, you change the nature of this equation to c equal to we have our integral of m dx, then plus, now that you've gotten the value of g of y from this equation over here, you now put it as f of y. So this theoretically should be how you are going to solve your problem. This should be the theoretical approach in solving your problem. So if I decided to solve for phi of x comma y by taking the partial integral with respect to y of n, that's dy. So what I'll get is phi of x comma y is equal to let me say I house this integral in a bracket, I'll now put my integration constant, which is going to be a function of x. So if my integration constant is a function of x, I'll now differentiate partially with respect to x, okay, because I want to determine the value of h prime of x. So it will be partial differentiation with respect to x of this whole stuff over here, then plus, when you now differentiate this, you get h prime of y, okay, h prime of x. So remember that from the definition of phi of x, when you differentiate phi partially with respect to x, you're going to get m. So when you equate this particular side to m, you will be able to solve for h of x. Okay, so let's say h of x has now been gotten to be something like a k of x, where k of x could be an exclusive function of x, or it could be a constant, or a mixture of a function of x and a constant. Okay, let's assume we have determined the value of h of x. So we'll now plug it back into this equation star over here, because this is what contains our solution. So you also have to recall at the same time that phi of x comma y is equal to c. It's a constant function. So in substituting all these values, c becomes, we have partial integral n dy, okay, then plus h of x. H of x is now going to be what? Since we determine the value of h of x from this point, we'll get k of x. Then yeah, that pretty much does it. So this is going to be your solution. So if you solve this, you will get the answer that you are looking for. You get the primitive form that actually gave birth to this differential equation over here. So this does it for the summary of the exact equation technique. I believe with the 4 examples we solved, coupled with this short explanation, you should be able to tackle any problem on exact equations. Okay, however, there are some equations that are not exact, so that one is beyond the scope of this particular subject for now, but in a future video we'll deal with non-exact equations and how to use integration factors to make them exact. But for now, master the steps of exact equations and you will be all right. Okay, this is the particular solution for the problem that we were given, and there's something I want to show you now. Okay, you can actually experiment this in other problems that I've given you, but what I just want to show you is that this is actually correct. Okay, this is correct. Okay, this is correct. So how do I prove that this is correct? So I'm going to differentiate it back. I'm going to differentiate this particular equation back, and after differentiating it, you will see that I'll get the original differential equation that was given to us. Okay, can we try that together? All right, let's go. So assuming you want to differentiate this one, you want to find dy dx for this particular implicit function. Now you have 3x cubed plus xy minus x minus 2y squared minus 2 is equal to 0. You want to differentiate it. The first step is to take everything to the left hand side, so you need to leave only 0 here. Now when you take this procedure you're applying, you apply it for all other exact solutions that you get. Bring everything to the left hand side. So after everything is brought to the left hand side, this whole expression is, just call it like a phi of x comma y. Just call it like a phi of x comma y. Is that okay? So remember, dy dx is minus partial derivative of phi with respect to x divided by partial derivative of phi with respect to y. Okay, so minus partial derivative of phi with respect to x. So we're going to differentiate everything here through with respect to x. So in differentiating with respect to x, we're going to get here 9x squared Then if you differentiate this one with respect to x, you get plus y. If you differentiate this one with respect to x, you get minus 1. So these terms, if you differentiate with respect to x, it cancels out since it's a constant, and this term also cancels out. Minus 2 also cancels out since it's a constant. So this is the satisfaction for derivative of phi with respect to x. So divided by, now I want to differentiate it partially with respect to y. Okay, with respect to y, if you differentiate it partially with respect to y, what are you going to get? So this one cancels out since it's a constant. X is a constant. When you differentiate this one with respect to y, you're going to get x. Okay, with respect to y, x is a constant. It's just like you're differentiating 2y and you get 2. So when you differentiate xy, you get x. So if you differentiate minus x, it cancels out since it's a constant. When you differentiate minus 2y squared, you get minus 4y. Is that okay? So when you differentiate minus 2, you're going to get what? 0, since it's a constant. So we now have that our dy dx is minus 9x squared plus y minus 1 divided by x minus 4y. Now if you rearrange by cross multiplying, you're going to get x minus 4y dy is equal to minus 9x squared plus y minus 1 dx. So when you rearrange 9x squared plus y minus 1 dx plus x minus 4y dy is equal to 0. So this is actually the question, right? Is that not the question given to us? Exactly. It's actually the question. Remember, we changed the structure of the question by using this minus sign to open up these brackets. Then we now got up to this extent. So this is the question, and we found the solution to be this over here. And we have now reproved that this solution is correct, it's unique, and it exists. So we have now gotten from the solution, we've gotten back the differential equation, okay, using the tricks that we established in the first two videos introducing exact problems. So this will do for exact equations. I want you to use this same technique to verify the solutions of other problems that we have solved so far in exact equations. Use the same technique to verify your solutions. Use the same technique to verify your solutions whenever you solve a problem on exact equations, and I believe you're going to be okay. So thank you for watching this video. Please like, subscribe, share, hit the notification to stay updated, and we look forward to seeing you on the next video. So we will put up some little more problems on exact equations, and we'll be looking forward to starting second order differential equations. To see second order differential equations, possibly Laplace transforms, the technique of using Laplace transforms to solve differential equations. So thank you very much for watching. Stay tuned, stay safe, peace.